Action. Okay, so hello everyone. So welcome to attend our this week Efficient AI seminar. And today we're very glad to have Professor Zirui from the Minnesota to give us this talk about the non-deterministic in the LLM. And Professor Liu is currently assistant professor in the computer science department at the University of Minnesota. And his interests lie in the broad area of the LLM and MLCs. He regularly published papers in top conferences such as NeurIPS, ICML, CLEAR, and MLCs. And his work has been integrated into widely used NLP tools like Llama.cpp SGLang and the Hugging Face transformers. It was highlighted at the Google I/O sessions. And actually, so maybe many of you know that. So Professor Liu, he proposed the very powerful KV cache quantization method, KV, and also recently, and he studied the non-deterministic issue of the LLM inference and training, and I think that already become got a lot of the attention and popularity in the community. And I think that is also his core topic in today's talk. So let's welcome Professor Liu to give us this talk.
Well, thank you, Dr. Yan, for the kind introduction. Yeah, today I will talk about my recent research line regarding the non-determinism and also the precision mismatch problem in the reinforcement learning, and also attach the QR code for the reference of today's talk. So all the code and all the materials they are in the link to this QR code. Oh, sorry. Okay, so this is today's talk outline. I will first talk about some background regarding numerical non-determinisms and why they happens and why in practice they are they are not they are something that we cannot avoid in practice. And later on, I will talk about our key finding regarding the impact of non-determinisms on the evaluation of large language model results. And finally, I will talk about some of the current process and the solution to these problems. So here we begin with the first part, the why we have the numerical non-determinism issue. So actually, I think this is both related to the system and hardware. So usually speaking, our computers they can only do the discrete calculation. That means although the numerical number or floating point number they are continuous, but the computer they can only represent them in the binary format. So one of the mostly commonly used the data format is often called IEEE 754 data format. So usually speaking, for the IEEE 754, you have three parts for your binary representation. First, the sign bit, which control whether the number is positive or negative. And then the exponential bit control the range of your representation. And finally, the mantissa bit control the numerical precision. So usually speaking, if you have more exponent bit, you can represent a more widely range of floating point number. And similarly, if you have more mantissa bit, you can represent the number in a more accurate way. So mantissa bit is like the resolution of your floating point number. So currently for machine learning model, one of the mostly used numerical format is bfloat16. It's often called Google Brain Float. So usually speaking, for all large language model you download from the website or the Hugging Face, they are using BF16 as the default precision. This is the context. And one widely known issue about the IEEE 754 is that actually floating point arithmetic, they are not associative. By not associative, I mean if you change the order of your computation, the result is actually different. So here I show one illustration. I show two illustrations to illustrate this issue. So you see if you change the order of the summation, like A plus B plus C is not identical to A plus C plus B in the binary representation. This is mainly because again, all the numbers they are discrete in a limited precision. So that means for all intermediate results, you need to do one rounding step. So that's the reason why you have this issue. So it's like the true arithmetic performed by the computer is like you have the round after A plus B, then plus C, then do another round. And similarly for this one, you first need to calculate B plus C, then do a rounding, and then you do another rounding between A and the intermediate results of B plus C. That's the reason why, usually speaking, for all IEEE 754 numerical format, they are not associative. They are not associative. So, uh, actually, this problem is inherent to all uh, computing issues if you use floating point number, right? So actually, this is not a new problem, and in the so for GPU programming, if you can ensure that the entire floating point order is deterministic, or if you can ensure that you don't change the floating point arithmetic order at all, you can guarantee your final results is bit by bit identical. But in practice, this is really, really hard. I can briefly talk about several reasons. So first thing is that because GPU they are doing parallel programming, they are doing parallel computing, right? So usually speaking, there are some cases each GPU thread they write to the same address sequence. They write to the same address. So usually speaking, for GPU they are using atomic address hardware primitive to do this operation. So you cannot predict which GPU thread finish early. So you cannot control the order of the floating point arithmetic in this case. Second, so actually for all GPU kernels, you have also the hyperparameter for them. So for example, for the general matrix multiplication, you have the hyperparameter called block size. So if you write CUDA, you will know what I'm saying. So like block size M, N, and K. So these are the hyperparameter for your GPU kernel. If you use different kernel, definitely your final floating point arithmetic order is also different. And finally, software and hardware difference. So hardware difference is more like fundamental. So for example, different GPU architecture, they actually implement different operation differently. So it's like if you use a up if you use Hopper architecture, then uh, the gene performed on the Hopper GPU is not the same to the gene on the MPage GPU. And also kernel they also behave differently, and the final accumulation order also change. And so just like I mentioned, this is a very old problem, right? So if we use computer to do the computing, then we have this problem. So this is not something new, and we already have lots of the efforts on this problem. So for example, if you are familiar with scientific computing or the HPC, you will know there are many existing solutions to this problem. One of a few most famous one is like Kahan summation. You can use you can like using an error compensator to compensate the error accumulation. And also you can use another thing is called the exact dot product accumulator. So their high level idea is that you use a very high precision internal accumulator to accumulate the intermediate results and finally convert it back to the low precision. This is actually already used in the in the NVIDIA GPU. So if you write the MATML kernel, you actually need to accumulate the results in the floating point 32 precision, not 16-bit precision. And also, actually, in the scientific computing, mm, one widely used technique to deal this problem is that you just use higher precision. You don't use low precision. So, for example, you can use double precision, or even 128-bit precision to do the scientific computing. That's the most easiest way to deal this problem. But I want to mention that this easy solution is is not suitable for the machine learning. situation because machine learning model they are already too big, right? So if you let alone double precision, if you use floating point 32 precision, then the cost of doing the inference or doing the training you cannot is not acceptable. So coming back, so this is for the algorithm size solution, and also actually NVIDIA also aware, or our scientific computing community also aware of this problem. So that's the reason why, usually speaking, we use another hardware primitive called FMA. FMA is short for fused manipulate and add. It's like you only do one rounding step for the manipulate and add operation instead of two. So if you don't apply FMA, you need to do two rounding steps, right? So because every time you generate intermediate results, you need to do rounding. So with FMA, you only do one rounding step to increase the numerical precision. Okay, that's already available in the current hardware. So I want to be clear. So what are available in current system? We already have the FMA, already have the exact dot product accumulator. But usually speaking, in practice, uh, uh, at least for the commonly used pipeline, we don't use Kahan summation. And also, actually, for non-mathematical operation, usually speaking, we tend to use high precision, like rotary precision embedding, layer norm, or softmax already use high precision. So but still, the problem is that for the most computation heavy operation, like mathematical, we need to use 16-bit precision. But but even with all these efforts, still it will cause huge variance by the numerical issue. Here I show one illustration example. Okay, so because like I mentioned, the floating point arithmetic is not deterministic. So that means if you change your evaluation configuration, the result is also different. For example, how many GPU you used for doing the model parallelism or tensor parallelism for your model, or if you change your evaluation bench size, or whether you use or what are the underlying kernel you used for doing the evaluation. They are all affecting your final results. So this illustration example is that for the DeepSeek uh, reasoning model, if you change the evaluation bench size from 8 to 32, it actually will flip your final answer, even if you use greedy decoding. Greedy decoding means you deterministically pick the next token with highest probability. So ideally, the graded coding should be deterministic. So that means no matter how many trials you run, the final result should be the same. But in practice, this is not the case because of the numerical issue. And this is for the reason, this is the problem with the inference. Here, this slide show the problem with the reinforcement learning. So because in reinforcement learning, usually speaking, you have two parts in your system. The one is rollout and the other one is training. You need to use rollout engine to roll out the experiments for accumulating the data for training them. But in practice, if you want to squeeze out your hardware performance, you need to use different software stack. So usually speaking, for the rollout, essentially you are doing inference. So we use VLLM or SGLang to maximize the inference throughput. But on the training side, because the workload is different, usually speaking, people use Megatron or SFDP to do the training. So, but different systems they implement the whole stack definitely different. So they implement the same operation in different kernel. And like I mentioned, there are some kernel mismatch problem. And why this problem is very important is that if you train RL, you want to make sure that the model give the same probability to the token in both the rollout and the training engine because they are the same token, right? Ideally, they should assign the same probability to the same token. But in practice, this gap is super large. So it's like uh, 0% to 100%. So if you change your serving system from VLLM to like training system SFDP, the token probability may just change from 0% to 100%. That will destroy your entire IO training process because In the IO, you need to use something called the importance sampling. Importance sampling, you need to calculate the ratio of the old policy to the new policy. But if you have this problem, then the importance sampling doesn't work, and then definitely your result is bad. So this is the background why this problem is why this problem is old but still very important and relevant to the current machine learning. And I think the key reason is that we cannot afford high precision. If we can like in the scientific computing community, we can use like double precision to do the computation. Then this problem can get significantly alleviated. Okay, I hope this part is clear. Okay. And also I want to this is more detail why in RL if you want to align them is very hard because they are completely different. So user being for the rollout, you have the prefill and decode, and also you got the KV catch, right? And for the training, you only have the prefill process, and this is the bench size misalignment. And also for the training and the inference, you need to use different parallel strategy. So for example, rollout, we often use tensor parallelism because decoding is memory bound. So we use TP to alleviate this issue. But for the training, because user speaking for training, we got a pretty large bench size. And also we don't have the decoding or KV catch. So user speaking for training, they are compute bound. We favor the fully sharded data parallel. And also, of course, they implemented the same operation differently. So that's the reason why user speaking for RL is very hard to align the training and rollout. And this slide is one illustration example of the rollout mismatch problem. Uh, uh, the, the, the practical impact of this problem. And also want to mention that for the mixture of Asper model, they are actually particularly vulnerable to the limited precision due to the router because router they are select token discretized, right? So you do the top K operation with the MOE model, and occasionally if you have the numerical issue, some token in different range, they may route to different aspect, then that will cause your entire um, uh, trajectory to be have different probability. So that's the reason why, usually speaking, for this rollout mismatch problem, it gets severe if you use MOE model, and it gets more and more severe if your model is larger. So for smaller model, actually this problem is not very significant. So it will scale with your model size. Okay, and here is some existing efforts to this problem, and people approach this problem from two directions. The first one is algorithm level solution. So algorithm level solution is like you can develop numerically stable reinforcement learning algorithm to accommodate the numerical error. So I think a few represent projects like GSPO, they calculate the sequence level importance ratio instead of token level, and also SAPO, similar idea, and also router replay. The router replay is, in my opinion, if you train large model with reinforcement learning, this is definitely the trick you need to employ. It's like you record the token expert routing in the rollout and reuse them or replay them in the training. So in the training, you don't let the router to do the selection, and also you can use 16-bit precision. You can use LP16 numerical precision in reinforcement learning. The idea is that, like I mentioned, the root cause of this problem is the rounding error, right? So, but the FP16, this numerical format have more multi-bit compared to BF16. So, you know, less rounding error. And also, we can develop some important, again, like I mentioned, why this problem is very important to IO is that they will destroy the important sampling procedure. So we can develop some algorithm to correct the token level sampling ratio. So This method is also widely used. It's often called TIS in this community, the token level importance sampling. So idea is very simple. You just calculate the ratio of VLM to the SFDP and reuse them in the IO training process. And I want to give a summary for the algorithm level solution. Their pros and cons is that their pros is it is lightweight, easy to try and implement. Just a few line of change, you can implement all of them, and they are minimal overhead, right? But the cons is that they are coupled with algorithm design. So that means uh, you cannot tell whether the final result is better. It's because they are more numerical stable or they are truly a better reinforcement learning algorithm. And also, they cannot solve the problem fundamentally. By fundamentally, I mean the gap is still the gap between train and rollout mismatch is not zero, right? So because the algorithm fix is ad hoc, uh, and you don't know whether for a new model or a larger model, it still can work or cannot work. You must run an empirical experiment to tell them. And and also we got the system level efforts. This is also the focus of this talk. Uh, this is already available in the inference stack like VLLM and SGLang. They are often called a deterministic mod. So the high level idea is that they build the deterministic kernel to accommodate the change of config, to change of the software configuration. So the good thing regarding the deterministic kernel is that they can solve the problem fundamentally. Fundamentally, I mean the gap is you can even theoretically prove that the gap is definitely zero, guaranteed. But everything comes with the cost, right? So the system solution is that because you change your all yeah, the your kernel, so they are very invasive. You change your inference stack or you change your IO stack completely from the kernel level, and it's pretty heavy, and you have large overhead because because determinism is like another level of constraint. If you want to if your kernel want to satisfy this constraint, you need to change the style of your kernel. Okay. So any questions of the first part, the walkthrough of the background, and also the why it is important to the IL and the inference?
I have some questions, but I think I will ask at the end of the talk. Yeah.
Okay, thank you. Then we come to the second part, our key finding on on their impact to the evaluation. So this part is almost all empirical study. Okay, we uh, just like I mentioned, the non-determinism will change your final results. Then one very interesting question to ask is that how severe it is for the numerical non-determinism to the inference stack, right? So we do lots of experiment to demonstrate this point. Uh, Usually speaking for LLM, their decoding contain two strategy. The one is degraded decoding. We choose the token with highest probability deterministically. And also we got the random sampling. The random sampling, they are like we sample the token according to the probability. So usually speaking in practice, we mainly use random sampling instead of graded decoding. Okay. And this is the setting. Because like I mentioned, graded decoding, they guarantee the results is different deterministic. So you're just speaking for the researcher or the engineer, we just report one single run accuracy with graded decoding. And for the random sampling based method, we report average accuracy or the pass at one. Like we run the experiment like given one single prompt, we generate a response 16 trials and calculate the average score between these 16 trials. This is the two commonly used evaluation protocol. And here we change the number of GPU version, and batch size to study how these factors impact the final evaluation results. And the long story short is that they significantly change your results. Okay. And I will briefly work through the results. So the first thing is that if you with greedy decoding, um, actually if you change your if you change the list configuration, your final output length is can vary significantly, like like 10,000 token variance. And also, your final evaluation results variance is also very large. So here the number is standard deviation of your final accuracy. So you see the final accuracy variation is around 10% for the commonly used numerical precision, like BF6, BF16, BF16. And this is pretty problematic. So that means if some researcher develops some new algorithm and the accuracy gap is less than 9%, this could be just from the hardware noise, not the true improvement. And for the random sampling, you see the variance is much slow, much smaller. And also, I think this makes sense because if you got some noise on your final logits, if you do the sampling, it's naturally robust to the sampling. Right, the sampling naturally robust to them. But here, I want to mention one more thing. I want to mention is that so you see. Uh, Even with a random sampling based method, the hardware change can introduce actual 0.3 to 2% variance. And in practice, I think this again a little bit problematic because if you are familiar with the p-value or p-test, you know that you need at least 2 sigma to demonstrate that you have your final improvement is significant. So 2 sigma means uh, two standard deviation improvement. So you see in this case for the AIME, if you run an experiment with 16 trials, you actually need 4 absolute percent accuracy improvement to demonstrate your algorithm is better than the old algorithm. But if you think about but if you actually think about what are the reasoning paper they commonly report, usually speaking for a reasoning paper, they don't report the error bar or the standard deviation. And second, usually speaking, they don't run the evaluation with so much trials, right? So they just run experiment like 4 trials or 8 trials and just report, okay, my algorithm is better than the STOTA by like 2 or 3%. So so this experiment tell you that the experiment results is not that trustworthy. So you need to uh, you need to spend more time on making sure your experiment setting is aligned. So I think DeepSeek, they really do the pretty good job. So DeepSeek run all experiment with at least 64 trials. I think this is a very this is makes sense. And in my opinion, we should run the experiment in this column. But because of the limit of the hardware resource, so usually speaking, for many researchers, they don't run experiment this comprehensively. So yeah, I don't think this is a good trend in this community. So in summary, we should run experiment with more trials and don't use greedy decoding. And run your experiment at least 16 trials, ideally 32 or 64. Don't run it just with 4 or 8 trials. And even if your final accuracy is better, it doesn't mean it mean nothing. And also report standard deviation. This is the lesson I learned from this experiment. And also want to give some insights. Why the large language model they are so sensitive to the numerical error? I mean, like I mentioned, this problem is already very old, uh, like more than definitely 50 years, right? And also for the convolutional network, we also have this problem. Well, why in the convolutional network, we don't um, we don't have many people study this problem? Why just LLM or even more accurate? Why just the reasoning model they have this problem? The key insight is that for the reasoning model, they have a they have so I want to be clear for convolutional network or BERT, they are just doing one step generation. They are now doing autoregressive generation. So for example, convolutional network, they just generate one single class label, right? And for the BERT, you also give the class label, like whether the sentence is their sentiment is positive or negative. And also for the before reasoning model, you also generate response, but in a relatively short number of tokens or a limited number of tokens, like no more than 100 tokens. But for reasoning model, if you think about it, they are generating thousands or even 10,000, 20,000 number of tokens. So at large language model, they have KV hash. At every inference step or every decoding step, you have some small rounding error in your KV hash, and they got accumulated across the generating step. So why reasoning is more sensitive? Reason one, they generate more token, and the error just get accumulated. At some point, they will cause the snowball efforts. And this is also the reason why in reinforcement learning, they are so sensitive. Because in the reinforcement learning, we are doing long horizon generation, right? Right. So in the agentic IL, we have the two calling trees, and it's super long. The reason one, this is the reason one. And reason two, I think, is more fundamental because the token distribution is different. So one motivating example is that imagine in what case the model is very robust to the numerical error. I think the answer is if your distribution is similar to one hot. So it's like you assign 100% probability to just one single token, and all other token they are all zero probability. In this case, even you have numerical error, they still just twist the distribution a little bit, right? So the probability, the highest probability, they maybe drop to like 98%, and all other they share the 2% accuracy, 2% of the remaining probability. But if you sample from this probability, still the chance is very high that you get the same results, right? But this is not the case to the reasoning model. Reasoning model, if you think about it, actually their distribution is more similar to the uniform distribution. This is the case for the reasoning model. So many tokens probability, they are very close to each other. We do the profiling, and we found this is the case for the reasoning model. And why this case, intuitively, they are very sensitive to the numerical error. To let's take the greedy decoding for example. Greedy decoding, they just pick the token with the highest probability, right? So that means they work by ranking the tokens and pick the top one. So ranking, but if you think about ranking is sensitive to the small rounding error if they are very close to each other. So imagine in this case, some small rounding error, they may change the ranking order. And this is the case happen to the greedy decoding. And also similarly for the top K and the top P sampling, they actually also rely on ranking because they, for example, top K means you only sample from the top K tokens, right? So in practice, K often set to 20. So that means you need to first ranking the token and select the top 20 tokens and do the sampling among them. So some small rounding error if they are very close to each other. That means in different run, you may exclude a different set of tokens. So in that I mean, so with top K, it's like in some cases, some token is in the pool, but in some cases, some token is not in the pool. But actually they are in the same decoding step. So that's the reason why sampling is also sensitive to this issue. And also give some insight why this happens. I mean, why after reinforcement learning they have this distribution? My hypothesis, and also I think this is where the chance is very high. This hypothesis is true. Is that in reinforcement learning, usually speaking, we are using GRPO, right? And if you do the reinforcement learning, if you want to have a high reward, you need to have, you need to do the exploration, right? You need to explore different reasoning paths in order to get the final, in order to get the final good answer. And if you want to do the exploration, that means you want your model um, to be uncertain regarding some token distribution. And actually, this hypothesis has been partially verified in related paper like high interface token or a minimal interface token. In I remember there is one research paper from Cuban or Quant team. They mentioned that they during the reasoning there are some very high entropy token. So high entropy token is very similar to this figure. So you got a very uniform distribution, and high entropy token actually will decide where the reasoning will go to or the direction. So I think the numerical numerical they are sensitive to the numerical issue. It's like a feature to the reinforcement learning. It is not a bug. So it is very hard to correct this problem fundamentally. I think the best way to approach this problem is that do a mix of algorithm solution and a system solution. That's my take. Okay, this is again a concrete profiling results. So to illustrate the practical the gap I mentioned. So again, the distribution is very similar to the uniform distribution, and you often got the unpaired top one and top two token. So a small rounding error may change the order of them, and then you have different reasoning paths. And that's our empirical finding regarding evaluation. And finally, I will talk about the solution to this problem. So solution to this problem is, like I mentioned, in RL, you can have the numerical stable algorithm. But for evaluation, uh, in my opinion, the only solution is deterministic kernel. And also deterministic kernel is also a fundamental solution to RL. Okay. And also I mentioned in the paper we changed the three configuration: evaluation batch size, GPU count, and GPU version. The first two problem we can have the deterministic kernel solution. I think the first one is the batch environment kernel. So this one is released by the Thinking Machine Lab. So they released the bash environment kernel. Their key idea is that it's like at the kernel level, they fully decouple the bench level computation. It's like they ensure that we are using data parallelism at the kernel level. So this is their high level idea. So if you can guarantee that different uh, instance in different sequence in the same batch. They do not interact with each other at all. You can make sure your kernel is batch invariant. The Yeah, this is how do the they implement the batch environment kernel. They propose the batch environment RSM norm, minimal and attention, and they fixing the reduction strategy, and the output they remain identical regardless of the batch size or the workload. And but again, like I mentioned, there's no free lunch. If you use this approach, uh, the batch environment minimal, their peak flops is only like 80% to your peak flops of your minimal. This is one illustration. You make sure your batch is fully decomposed, and you make sure your reduction is irrelevant to the batch size. And later, this work is developed in my lab. We developed the TP environment kernel. TP environment kernel means no matter how many GPUs you use for tensor parallelism, your final results is guaranteed to be bit by bit identical. Our high-level idea is that we ensure that your GPU, your math-mode accumulation, and the all reduce uh, order follow the same binary reduction tree. This is our high-level idea. In this way, if you change the number of GPU you have, you still got the same summation order, like at the right side, because they are following the same tree structure. So the challenge here is like you need to align the computation outside the GPU kernel and within GPU kernel. I think this is pretty hard, actually. And we spend lots of the engineering efforts to implement this system. But from the algorithm level perspective, it is pretty easy and intuitive. You just make sure that they follow the same binary tree. Okay, this is the tensor parallelism invariant. What we call it TP invariant kernel. So how it works? Uh, the short answer is pretty good. We use both the batch invariant kernel and TP invariant kernel to RL, right? So because if you recall for the RL, the problem is that first you have the batch size misalignment, and also you got the TP size misalignment between rollout and training. And we patch this set of kernel to both the inference stack and the training stack. Finally, we obtain the zero probability gap between rollout and training. So you see for the line, like let me check the green line you see here, the KL divergence between the train and the rollout is a straight line. That means it is zero. So and also you see if you guarantee or you don't have precision mismatch, actually your reward will grow faster. Your training is more stable. But again, there's no free lunch. With this approach, you see, our method introduce significant overhead. It's like 50% overhead compared to the baseline. So again, no free lunch. So that's the reason why I think in the future we should approach this problem from both algorithm and systems side. So no single one can rule out this game. And the takeaway for this talk. So numerical stability is a long-standing problem, but why reasoning model they are more sensitive? The reason is that there are lots of the high entropy of the minority token and the error accumulation. Second, what factor can impact the results and introduce actual variance? Actually, anything that will change your arithmetic order will change your results. So, I mean, like GPU version, software version, the number of GPU you used for parallelizing the compute, battery size, lots of different efforts. Okay. And what are the potential solutions? Algorithm fix and a deterministic kernel, and at least up to May 3 band. These are the only two solutions. Oh, I want to mention that actually there is another. So actually before IEEE 754, we got another numerical system. I think it's called uh, POSIX. I'm not sure whether I pronounce it correctly. So it's like they are not using the IEEE 754 numerical format. It's a completely new uh, data format. But why I only mention it in the end is that although if you do the computation in this numerical format, you can guarantee that your computer is deterministic. But the problem is that currently no commercial hardware implement uh, this strategy. So it is largely still a research topic in the computer architecture and the and the and the high performance computing community. So it's not commercialized. So we cannot test them. Okay. Uh, that's all. Any questions?
Yeah, first, thank you, Zirui, so much for this wonderful talk, and I think we already have some questions in the chat box, so maybe you can check.
Sure. Regarding token probability for reasoning model, did you observe similar trend across various model and any specific behavior with dense versus MOE model? Yes, yes, similar trend. And again, like I mentioned, I think this problem is like a feature of IL. So it's not specific to the model family. If you use IL, you got this problem. But MOE model is more sensitive to IL. So if you are curious, you can search. There is one paper called uh, uh, I think it's called R3. So it's like the router replay that paper. And it's already the default stack in the current IL. Oh, the second question is that do quantized model that rely entirely on integer uh, produce invariance? Very good questions. Actually, we do this. Actually, we also do this experience. The final answer is no. I don't. I don't. I found that even after quantization, you still got a very large variance. I think the key reason is that for quantization, actually, there are two paradigms. The first one is weight-only quantization. For weight-only quantization, you still do all the computation in floating point number. So that means if you do weight-only quantization, the result is the same. And the other one is paradigm like smooth quant. You quantize both the activation and the weight into into the integer number, and you do the mathmal in integer number. But I want to be clear, with this paradigm, actually only GEMM is done in integer arithmetic. For all other operations you still do it in floating point number, like a rope, layer norm, and the flash attention. So and also KV cache. So in practice, my observation is that there is no help. So the variance is still pretty much the same. Any other questions?
So maybe I think I can first ask some questions. Yeah.
Sure.
So first, I think so this slide shows that so you think that the fundamental potential solution is that to use the deterministic kernels and the algorithm fix. So here, when you refer to the algorithm fix, you mean that we need to like to change the underlying the processing mechanism of the inference or something else.
Oh, oh, sorry. Last slide is the QR code. Algorithm, I mean give me a second. I mean the solution like this. You develop some new reinforcement learning algorithm like GSPO. So I think if you read the GSPO, their main motivation is to make sure your IO is more stable.
Okay, so
This
that
is
means it's still kind of
oh
I think it's still kind of built on top of the like the sequential decoding, right? Or the greedy decoding, right?
correct.
Do
Kind of
you
correct,
think
correct.
kind of possible is that if we find some kind of alternative solution that's like the beyond or to change the grid decoding at the bottom level, try to mitigate this non-deterministic issue?
Uh, I think it's pretty hard. The reason is that so if you think about it, uh, this problem is getting severe because uh, you got the error accumulation across token, right? And so it's related to KV cache. But currently, no matter so the current the most widely used paradigm is first autoregressive. You got the KV cache, and second diffusion language model. And diffusion language model actually, if you want them to work well, you also need to use KV cache. So at least for these two mainstream model, we have KV cache and we have this problem. And if we want to completely get rid of this problem, we to be honest, I don't know. I don't. I'm not sure. Uh, if we can come up with a new paradigm, completely get rid of the KV cache, and if we can generate multiple tokens together in one single forward pass, maybe this problem can get better. That's my feeling.
Okay, thank you. And another question is so you mentioned that so after the mitigating this issue using, for example, the tensor environment or the batch environment kernels, the kind
Mm.
of penalty is that the overhead like around 50% overhead.
Yeah, yeah.
in that table. Yeah. So can you elaborate a bit more? So how this kind of overhead come out?
Oh, very good questions. I can give I can give a quick idea why this is uh, a very large overhead. So first thing, I think first example is flash attention. So first thing is that if we don't want to have the deterministic flash attention, you just use the vanilla FA, right? FA is short for flash attention. But if we want to making sure uh, they follow the same arithmetic order, you need to fix the I think the hyperparameter is uh the tile size of your flash attention. It's like in practice, if I recall correctly, bash environment kernel they fix the token size is 16. So that means no matter how long it is for this sequence, the tile size is 16 tokens. But in practice, if you don't use deterministic kernel at all, they can change the tile size according to the hardware and also the workload. So to fully utilize all the streaming processor. So usually speaking, for this deterministic kernel, you cannot use the optimal configuration. That will significantly slow down your inference process. So imagine you got a super long contest to do the inference, but you only but the tile size is 16. It's like your hardware utility is very low. This is the reason one. The second reason is that, for example, for our TP environment kernel, if you think about it, if you want to do the tree reduction, you actually need an actual buffer to store the temporary results. So that means when you write the kernel, you actually need to use more very precise on-chip memory resource. So that means you need to fundamentally change the how you write the MATML kernel. So we actually for this TP environment kernel, even if we optimize it very severely, it still can only reach, if I recall correctly, only reach the like a 50 to 60% of the peak flops of the original MATML. And again, you need to patch all of them to both the inference and the training, and it will significantly slow down both sides. So that's the reason why I think it's better to use both solution together, not only one, not only just the system solution or the algorithm solution.
Okay. So from your description, it seems that if you put kind of more engineering effort that so we can further like to improve the performance of the TP environment or the
Yeah,
environment.
I think so.
Oh,
Yeah, I think this is already happening. So like I know SG Long team, they work pretty hard on optimizing the 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 overhead of the bash environment kernel.
okay. I think there's another questions in the chat box.
Oh, I'm not sure how to pronounce it. I think it's spelled as I think it's like this one, 4 6
I think
or
it POSIT.
oh I see. Yeah, this one. This
Yeah.
one actually, if you are familiar with it, it can guarantee your final results is deterministic. But just like I mentioned, there is no commercialized hardware support this one.
Yeah, as I know, there's some kind of the stock company that proposed some this number presentation, but it's kind of very early stage. Yeah.
Yeah. But again, this could be a fundamental solution to this problem, in my opinion.
Yeah, the issue is that whether it is worthwhile to like to invest a lot of the kind of the changing costs to do that from the chip industry. Yeah. Yeah, that is an issue. So any other
Yeah,
question?
oh, yeah. Sorry, go
Go ahead,
ahead.
go ahead.
Oh, I just want to mention that I think it's pretty hard for the for the hardware company to adopt this because I think this is you need to completely change your hardware stack. I mean, if you don't have a significant benefits from bringing this numerical format, it probably won't change the hardware industry. This is my opinion.
Yeah, I agree. Yeah, yeah. From the perspective of the hardware design, so they don't have kind of sufficient incentive to do this. Yeah.
Yeah.
So, any other questions from the audience? So I may have one last questions. Yeah, if nobody asks question. So do you think that it is also possible from some other alternative strategies, like for example, we can do some kind of the intermediate monitoring of those that accumulated error during the reasoning process? Is that kind of the potential kind of lightweight online monitoring?
Yeah. Yeah, actually, I also thinking of this problem. But I think this is pretty hard to do. This is mainly because it's very hard to define. So if you want to deploy some monitor, you need to define what is outlier, right? But for this one, it's very hard for you to define how you tell something is going wrong from the normal point because you don't have the ground truth label, right? So you cannot run the experiment in floating. So if you say the results is different to the floating point 32, then that means you have a your error. Uh, but you are not affordable to like run it in 32 bit first. Yeah, that's my feeling. It's pretty hard to do. But if we can do that, this is probably a very good idea.
Okay. Okay. Got that. Okay.
Yeah, I see two new problem. I will give a very short answer to them. First one is that under different concurrency, will the order of the T1 to T8 would keep the same? I think the short answer is that we won't let this situation happen. We don't use automatic add. We make sure that they under the same concurrency. This is short answer. So they are still the same. Second answer, yes, I read the LLM 42 paper. I think, yeah, this paper is very, very good in my opinion. I pretty much love this paper. And I think using the speculative execution is a brilliant solution to this problem. That's all my comments.
So, any other questions? Okay, actually, so this question is what we just like to ask. So, whether do you think like those the speculative execution decoding based kind of strategy may can help mitigate the
Yeah, I think so. I believe this is the right direction.
okay. Okay. Okay, thank you so much. So actually I have some other questions, but I think I don't want to to keep you that
I
so
see.
long. Maybe we can discuss offline. Yeah. Yeah. So
Yeah,
again, so thank you everyone for your for attendance and thank our speaker again for a wonderful talk. So Zirui, thank you so much. Yeah. So our next talk will be the next Tuesday. Okay. So thank you everyone for your attendance. So have a wonderful day. Thank you, Zirui. Thank
thank
you.
you. Bye.
Have a good one.